or was it this track, represented the positron? Whichever one it was, at that point, the positron had come. Let's assume that it was this one. I really can't tell from the simulation. But let's assume that this was the positron. The positron came to rest. At that point, the positron combined with an electron in the sample, and they two annihilated each other, producing what is called annihilation radiation, two photons, each of energy 511 kiloelectron volts, that went off in opposite directions. One of them went down this way, and because of what I do about the average number of photons, I pretend that another one came in at the top. This one went out through the top, and I assumed another one came in at the bottom, and then finally left. Let us see how important the effect of subsequent interactions actually is. I'm going to do another photon simulation. I'm going to use 100 kilovolt photons again. I'm going to start with a random number where I know what happens. And first I will show you what happens if I don't include the subsequent interactions. And so we will run 25 photons for one screen. Now I'm going to include the subsequent interactions. So I'll check that box. I'll have to set my random number back to 2. And now I will run the same thing. And what you will see when I do it is that these initial interactions represented by the dark blue photons are exactly the same. But now we have these subsequent interactions taking place for each one. And it's taking longer for the simulation to appear on the screen because the MacDose has to do a lot more calculation in this case. That's a rather busy screen, but it's pretty clear that a lot more interactions took place. In order to make the screen not be so busy, let's go back and set the parameters so that we only show the electron tracks. And the first time I'll do it, I won't include the subsequent interactions. So we'll run those same 25 photons without including the subsequent interactions. And there you see where the electron tracks were. Here are the electron tracks with subsequent interactions included as well. You can see how much more energy has been transferred to the electrons by subsequent interactions. Also, notice that there are more electron tracks near the entrance side of the phantom than there are near the exit side of the phantom. The skin dose is greater than the dose deeper in the phantom. The simulation, including subsequent interactions, has been repeated now for 250 photons instead of for 25. Here again, it is much easier to see that there isn't as much dose over here as there is at the entrance side. Here are the electron tracks, including both primary and subsequent interactions, for 1.25 MeV photons, the energy of the photons from a cobalt-60 source. The electron tracks are more uniformly distributed throughout the sample, and they are, of course, longer. And here are the tracks from 8 million electron volt photons. There is much more energy deposited in the deeper layers of the phantom than there is in the entrance layer. If we imagine a tumor that is some distance below the skin, then the skin dose is much smaller for a given tumor dose when we use these higher energy photons. We can see this if we look at a plot which shows the relative dose versus depth for photons of these three energies. For the lowest, the 100 kilovolt or ortho voltage, the entrance or skin dose is higher than in the deeper parts of the phantom. For the cobalt-60, the depth, dose versus depth is roughly constant. And for the 8 MeV photons, the dose increases dramatically with depth. These plots are for a parallel beam of photons, which means the source to skin distance is infinite. In actual practice, the dose falls inversely with the square of the distance from the source. Let us review what we have learned. We have seen that photons can transfer energy to electrons by the photoelectric effect, by Compton scattering, and by pair production. The individual interactions are statistical, and the fraction of photons interacting fluctuates. The average fraction of photons surviving a distance x is given by e to the minus mu x. The effects of X-rays are caused by the energy which they transfer to electrons. The energy can be transferred to electrons in one location, and the electrons can then travel to other locations, losing their kinetic energy as they do so. New, lower energy photons are produced in Compton scattering and from pair production. These subsequent photons also interact and in turn transfer energy to electrons. Photons of high energy deliver more dose deeper in the tissue than photons of lower energy.